All right. That's circuits 2. We don't want that. I thought I had it open. Maybe not. Okay. Did I save over it? That would be just like me. Well, I know where I posted it. Let's get it there. All right. So we're going to start with charge and current. And just some of the basics. Make sure you know these because I have been surprised by people in circuits who didn't know some of these things. So we want to make sure that we know them. So the symbols and units for charge and current. So symbols and units for charge, what would that be?
C, it's a coulomb.
So we've got coulombs. So that is the abbreviation, but it's usually not the symbol we use for charge. The symbol we use for charge is Q. So for charge, it's Q, and units are coulombs, and current is I, measured in amps or milliamps. And I am the worst at this, but usually, like the way that your book does is that if you have DC current or current that's not changing, you use capital I. And if you have a current that is changing with time, you can use a lowercase I, but I am really bad about that. I use both, so but that is, some of the difference. And an amp is actually the fundamental unit. So the amp is actually the fundamental unit, and the coulomb is actually the derived unit, which is kind of interesting. But what is the definition of current?
Charge per unit time.
Yeah, and what does that mean? So we had that it's dq dt, or the derivative of charge with respect to time. And what does that mean? Is charge just popping up and going away? How do you have charge per unit time? How does that make any sense?
It's the flow of electrons, right?
Well, the flow of any kind of charge of current, any charge carriers. So this is like the flow of charge carriers, and specifically in electrical engineering, current is defined, the positive current is the flow of positive charge carriers. Now, when this was first defined, there was no way to tell whether it was positive charges moving in one direction or negative charges moving in the other direction. And it turns out it doesn't matter. Everything that we do works the same regardless. And so our current, the way current is defined, is the flow of positive charge carriers. That's actually not what's happening. It's electrons that are flowing in the opposite direction. But when we talk about a current, if I say the current is going to the right, that's as if positive charges are going to the right. And that works, it ends up working just fine. How do you calculate current given a function of charge? So if I have, for some reason, a function Q of t is the amount of charge I have at a given point and at a given time is e to the 2t, and I want to get the current is going to be the derivative of that. So dq dt, or I, would be 2e to the 2t. It'd probably be negative, because you wouldn't have an exponential growth of charge. How do you calculate accumulated charge given a function of current? So if charge is dq dt, then if you multiply both sides by dt, and you get I dt equals dq, and you integrate both sides, you get that your accumulation of charge is going to be the integral from time 1 to time 2 of I dt. And we'll have a problem with that later on. And that was part D. Okay. Any questions on that before we go on to the next part?
See, whenever we see Q of T, that's usually a derivative.
It usually means that you're... Yeah, I think what you're asking is usually if you see Q of T, probably what the problem is asking you to do is to find I of T, and in which case you would take the derivative. And usually if you see, well, I don't want to say that that's always going to be the case, because there's another thing that could be true. If you have I of T to find charge, you would integrate. But there is something else you might do, and that's because power equals current times voltage. So it's also possible that if you had I of T and V of T, you might have to multiply them to get the power as a function of time. Because I've seen that too. So those are the sorts of things that you might see. Yeah, all right. Was that the answer to your question?
Yes.
Okay. All right. All right, so here is a problem. We have the current that's given as 0 for time less than 0, and then 20e to the negative 5,000 t amps for t greater than 0. So less than 0, our current looks like this, and then at 0, it's 20 amps. And then it's e to the minus 5,000 t, so that means it's decaying exponentially to 0. So it says calculate the total charge in microcoulombs entering the terminal at its left, entering the element at its left terminal. So that would be, our total charge would be the integral from 0 to infinity of I of t dt. In physics and engineering, they don't seem to mind if you stick infinity up there as a limit of integration. In math, they don't like it, and they want you to put like a and then take the limit as a goes to infinity, but we'll do it this way. So 0 to infinity of e to the 20e to the negative 5,000 t. dt. And just in case you have forgotten from your Calculus 1, if I have the integral of e to the t dt, that's just e to the t. If I had e to the 5t dt, that's going to be e to the 5t over 5. The way that you learn it in calculus is by doing a u substitution. But anytime what you have up here in the exponent is just linear, it's just going to be the coefficient in the denominator. So the derivative of e to the 5t, so if I take the derivative of e to the negative 2t, for instance, that's negative 2e to the negative 2t, and the integral of e to the negative 2t dt is e to the negative 2t over negative 2. The same works with sine and cosine. This is just your helpful hint for the day. Sine of 5t, if I take the derivative of that, that's 5 cosine 5t, and the integral is negative cosine 5t over 5. So when you integrate, that constant term in front ends up in the denominator. So what I'm going to get when I integrate this is 20 e to the negative 5,000t over negative 5,000 from 0 to infinity. So I'll take 20 over negative 5,000 outside, and on the inside I get e to the negative infinity minus e to the 0. So that is negative 0.004, and e to the negative infinity is 0, and e to the 0 is 1. So this is 0.004, and since my units up here were amps, then my units here will be coulombs. If it had been milliamps, my units would be millicoulombs. Oh, but it says calculate the total charge in microcoulombs entering the element at its left terminal. So microcoulombs is, a micro is times 10 to the negative 6. So I would get I don't know why we would want to have this in microcoulombs. Seems like millicoulombs would be more reasonable. But no, that's it. Okay, so 4,000. So multiply times 10 to the 6, and you get 4,000 microcoulombs. And was there another problem here? Yes. No. Was that the only problem for number 1? It was. Okay, so any questions on that before we go on to number 2?